Okay. So today we'll do without break. Okay. So we discuss rigidity theorems and applications. We're just reading Margulis lecture note for its Abel-Price talk, and a lot of people, it's very similar to what we do here the last time. From his point of view, more interesting. But he discussed a lot Selberg local rigidity. Let me remind you, local rigidity was proved by Selberg, Calabi and Whale. So Selberg was the first for SLN, and few years later, in a more cohomological or geometric, essentially geometric method, Whale generalized it to general Lie groups. So the theorem is to let G be semi-simple. I should write. It's readable? Yeah, it's readable. And let gamma in G.
It is readable. As readable as ever.
Not more readable?
No, but it is readable.
Gamma, a uniform lattice such that which project densely, let's say, which projects densely to every, let's say, three-dimensional factor. So G is a product of, eventually a product of simple groups. And if you have SL2 factors, then you want gamma to be irreducible in that factor. SL2 is the only number. Sorry?
SL2R, right?
SL2R. Then gamma is locally rigid. What it means that i.e. if F from gamma to G is close to the identity, it's close to the inclusion, it's sufficiently close to actually you can state it in the following way. So if if T goes to Ft, it's a continuous deformation. This is an element in form gamma G. This is a topology for presentation variety. So this is a curve such that F0 is the inclusion. F0 of gamma equal to gamma. Then there is a map there is GT. There is not a curve. T goes to GT. Such that Ft of gamma equals GT gamma GT inverse for every gamma. So any small deformation is a conjugation, and Okay, we stated it a bit differently. We didn't stay with a continuous curve, but just but it's equivalent. So that's a local rigidity, and the motivation of Selberg was the first corollary, which we discussed last time. There is G such that G and G gamma G inverse is contained in G of K for some number field. Okay. There is a finite extension of Q such that, so G is a group of matrices. We suppose that G is, let's say, adjoint same thing. U group. So that's the constant, and that was Selberg's motivation. Actually, that was Selberg, I think, in his paper from 1960. It was very influential. Actually, I knew it, but in Margulis' lecture notes for the Abel Prize, he emphasized it a lot that this paper influenced both him and Mostov for the strong and super rigidity field. So Selberg, his motivation was not to prove local rigidity, but to prove this state. And then this makes him conjecture the arithmeticity conjecture, which Selberg's conjecture. So did we discuss arithmetic groups already?
No.
No, not enough. Okay. So actually, Selberg conjecture. Let me state it in the following way for the moment. So he conjectured that actually all eigenvalues of elements in gamma are algebraic integer. So Selberg conjecture, maybe let's say for SLN, where n is at least 3. But a conjecture, of course, in a more general way. So actually, that was more or less his conjecture. So no, actually, he conjectured that the conjecture was split in the case of non-uniform lattices. He actually conjectured that there is a rational structure for the Lie algebra, an integer structure with respect to some base. Gamma must be commensurable to GG. I will discuss arithmetic groups soon. And in the uniform case, he just conjectured that all eigenvalues must be algebraic. And later, Petetsky Shapiro corrected. Okay, this conjecture turned out to be true, but some stronger statement, which is we will discuss soon. Actually, why not do it now? I wanted to discuss also the other application, which is one finiteness theorem, but let me say a bit about arithmetic group, because some of that was the motivation.
Did you say how to get from local rigidity to the column?
I explained it last time. Yeah, this was last time. Basically the context of last time. So basically, it's a consequence of the implicit function theorem. Basically, you say that if X is an algebraic variety which defined over Q, then if Q bar, so the algebraic, the real algebraic vectors are dense in X. So this is a real algebraic variety which defined over Q, and this is the topological closure, and the Hausdorff closure, and this is the algebraic closure. This is a statement that you prove it follows from the implicit function Q1. And once you use it for X, which is gamma G, so this is the algebraic variety which is defined over Q. If G is a semi-simple algebraic group, then it's a real algebraic group, and the representation variety is an affine algebraic variety. And so if you use it here, and inside it you have the inclusion gamma into G, you call it I0, and so near I0 you can find another homomorphism which is with the algebraic values. It goes into the algebraic. Now then you prove that if you have a co-compact, discrete co-compact subgroup, then a small deformation is still discrete and co-compact. This is something that you have to prove, and okay. Actually, no, we don't need it here. No, actually, I don't need it here. So it's follows from the local rigidity. It's true what I said, but it's more than that is true. So if you have a penny, so there is, by this statement, there is F close to I0 such that F of gamma is contained in G of, let's say, Q bar, and by local rigidity, this comes by conjugation. And since gamma is finitely generated, you don't need Q bar, but you need some finite extension of Q. And that's how Sandberg deduced this corollary from his local rigidity theory. Let me discuss a bit arithmetic groups, and then we come back to at least define what is an arithmetic group. So, say groups and the Rigidity conjecture. So, okay. So let's G be algebraic defined over Q. Actually, okay, let me just define it. Sure, let's do it. So let G be, let's say, a Lie group. Gamma in G is called arithmetic if there is a Q algebraic group H, so it's a algebraic group defined over Q, and a surjective map F from H, from the real point of H into G, with compact handle. Such that H of Z, the image of H of Z, is commensurable Commensurable means that the intersection, two groups are commensurable if the intersection is of finite index in both. So did we discuss this notion in this course?
No.
Not yet. So, so let me just
You by default assume that G's are joined.
sorry?
You by default assume that G's are joined.
No. So here I don't assume anything. This is just this is a definition. I don't assume anything and I don't state anything. It's just this is how I define arithmetic group. So gamma in G is called arithmetic if blah blah blah. So just remarks about this definition. So gamma 1 and gamma 2 inside the group G are commensurable if the intersection gamma 1 gamma 2 is of finite index in each. Now, if one of them is a lattice, then it's enough to state that it's finite index in that one, and then it will follow that it's finite index in the other. So here is this elementary exercise. Yeah. If gamma 1 is the lattice and gamma 2 is commensurable, then gamma 2 is the lattice, and if you want the co-volume, gamma 2 is equal to the co-volume, or the co-volume of gamma 2 is related to the co-volume of gamma 1. By the index of the intersection. So the ratio between the co-volume is opposite to the ratio between the index of the intersection. So if one is a lattice than the other. So of course, if we discuss a group and we call it arithmetic, we want finite index subgroup of it to also be arithmetic. Like example of a group which is we like to think of the arithmetic group is Ethel and Z, but we also want to consider finite index subgroup of it as arithmetic, and you also want to allow finite extension. So arithmeticity is a property of commensurability class.
This is just because you want the definition to like satisfy the theorem?
No, it's more than that. It doesn't make sense if you don't require it, because what is H of Z? H of Z is not well defined actually, because when I say that Q algebraic group, it comes with some rational structure, but it doesn't come with a Z structure. But H of Z is only defined up to commensurability. So when I give you a rational algebraic group, then the group of integer coefficient is also only defined up to commensurability. So even to make sense of what is H of Z, I need to say what is commensurable. But okay, this is one.
So what algebraic groups reject under the universal cover of conceptual?
Sorry.
What algebraic groups reject or they tell me to? I mean, suppose G is a universal cover of conceptual.
And which H do you choose? Which F?
Okay, yeah, if you want, let's say the universal color of SL2R is a group that we like less because it's not algebraic, but let's say the universal color of SL3. That's just two cover of SL3, and it's still algebraic. But usually H, how you should imagine H of R will be something of the form G cross K, where this is compact, and this will be the kernel. H will be some extension of basically G times something. Maybe I will give example.
So you can't use this definition for non-algebraic groups, right?
Sorry?
So you can't use this definition for the universal cover of SL2R?
You can. I don't know if you can think of it. So another exercise.
So the previous one, you wanted us to find the equation in covolumes.
Sorry?
So you want us specifically to find the equation.
Yeah, it's one line. Okay. And another exercise says that if you have a map from H to G, you have two Lie groups, or two locally compact groups, and you have a surjective map. Compact kernel, you have map from H onto G, which compact kernel, and you have and gamma in H is the lattice, then f of gamma in G is the lattice. So if you have a map from one group onto another group, yeah.
It's definitely, and I think it doesn't have to be discrete.
If you have if K, if this is compact, it's surjective and compact. So K compact, F surjective. Like in the theorem. Then the image compactness kernel cannot destroy its fitness, so the image will be discrete, will be closed. I mean, whenever you have a closed, so this is a closed map, as we know. So if you have the, yeah. So that's why we allow compact kernel, and basically, okay. So this is the definition of arithmetic group. Let me give you an example. Okay, I'm diversing from.
Sorry, in the exercise K is the kernel of F.
Yeah,
The image of.
Yeah, that's how we denote short exact sequence. So
yeah, it's a short exact. Okay, okay, yeah, okay.
Yeah. So and let's give some examples. So So of course SL and Z decide SL and R is an arithmetic group. It's like a canonical example. Here is another example. So consider the form Q, X, Y, Z. The X squared equals Y squared plus square root of 2 Z squared. That's a quadratic form. And then let's say consider the group O. Consider the group O of Q, of Q, the orthogonal group of Q, which is all the matrices that preserve this this quadratic form. So all let's say G inside SL3 R such that U of G of the vector x, y, z is the same as U of x, y, z. Or if you want all the matrices such as G transpose 1, 1, square root of 2, G preserve this form. So this is okay. No, I don't want to see. Yeah, that's not necessarily in R. Let's say. Okay, otherwise, we just so okay, and now okay, so this is a extension of degree 2 over Q. So there is a procedure that to view this group as a Q algebraic group instead of a K algebraic group. It's called the restriction of scalar.
Which is K, which is
K now K is the
just a zero.
K is the extension of Q by square root of 2. And there is a procedure of restriction of scalars, and yeah, I didn't want to go into that, but let me just do it very shortly now. So there is a procedure of restriction of scalar, and then you get a group H, which is defined over Z, and a group defined over Q, such that H of R will be the group SO21 plus SO3, which is compact, and H of Z is a discrete group. Is a discrete group in the product, which will, if we map it, if we quotient this into SO21, then this discrete group goes into a discrete, actually co-compact subgroup in that group. Okay, I say it very briefly. Let's discuss. I'll give example. I'll discuss example of arithmetic groups at some lecture in the future. So, but this is
What
just
is gamma again?
what?
What is gamma again?
Gamma, if you want, inside this group, gamma will be isomorphic to the group of O of Z square root of 2. In that group. It is just this group, but when you view it inside H, with respect to a procedure that is called restriction of scalars, then gamma will be the integer point. Intersection of H with SL and Z with respect to sign varying. So gamma will be HZ, and this is, I wanted to give this example just to explain where the compact factor comes. But I don't want to go into details. I want to mention it very briefly. At the end of the story, we get a group that we know a lot about it. It will be a suffix group. It will be a, okay. I'll come back to this and other example later. Let me just tell you the story of arithmetic groups. So let's start with Borel-Rishander theorem, although it started much earlier, but Borel-Rishander theorem says that let's say let G be Q algebraic group and without Q maps to R. You don't have, let's say if G is semi-simple or perfect, then it's fine. But you don't even need that. You just need that there are no maps into the real, no mobilization, which are defined over Q. So unipotent groups are also allowed, if you want. Then G Z is a lattice in G. So arithmetic groups are lattices. That's Borel-Rishander theorem. Under this very weak assumption, which is necessary, that you don't have rational maps onto the real, onto the multiplicative real, then GZ is a lattice in G. In G of R. And they also say when GZ is co-compact, so GZ is uniform if and only if GZ has no unipotent element. So if they are unipotent, then we know it cannot be
So only if you are the
GZ. So moreover, GZ is non-uniform if and only if it admits non-trivial unipotent. In the original paper, the condition was if G of Z is co-compact, if and only if there are no co-character which are defined over Q, but you can show that it's equivalent to the existence of unipotence.
The first statement is not definitely, right? You can find Z lattice in the R structure, even though there are Q maps to.
The theorem is that it's a lattice. So let's say, let me state it. Let's say, let G be a semi-simple Lie group which is Q algebraic. Actually, every, let's say, adjoint semi-simple Lie group is such. The adjoint of the semi-simple Lie group give you a rational structure. So it's not very restrictive. So it's true for any semi-simple Lie. The version that I stated previously was slightly more general and also applies, let's say, to unipotent.
What was the thing about co-character is equivalent to non-trivial unipotence?
Sorry?
You said something is equivalent to.
Yeah, I said it, but yeah. I just say this condition somehow is more suitable to us, but in the original paper, you cannot find this condition, but you can find another condition, which is that the G of Z is co-compact if and only if there are no rational co-characters, which mean maps from the multiplicative group into G, which is defined over.
Wait, the maps are into the multiplicative group or from the multiplicative group?
Before was from the multiplicative. Okay. Now there is a completely different version of the statement. But before, the statement that was written before is that GZ is a lattice if and only if there are no Q characters. So map from G to the multiplicative. Right. And it's uniform if and only if there are no Q co-characters. This is uniform here.
There is a group with no characters and yes. And yes, co-characters. A group with no characters, but yes, co-characters.
Sure. I mean, yeah. I mean, yeah, this is another theorem that I mean, every semi-simple group has plenty of non-uniform lattices and uniform lattices, which are arithmetic. The non-uniform comes from structure without co-character, and the uniform comes from structure with co-character. So that's the Borel-Richano theorem, which is quite an amazing theorem, and my plan is to prove it in this course. Actually, I plan to do it much earlier, but somehow, okay, we will come to it maybe next week. I want to prove this theorem. So basically, it says that GZ is a lattice in G of R. And then if you have a map with compact kernel, then the image is still a lattice in the image. So that's Borel-Richano. And then the arithmeticity conjecture, Selberg and Tsachik Shapiro. Okay. Let's write like this. The Tsachik Shapiro conjecture that in higher rank, when G is rank at least the opposite is also true. Every irreducible lattice is arithmetic. So actually, Selberg conjecture that every non-uniform lattice is arithmetic in the sense that there is a rational structure such that it's measurable to G of Z. And for uniform, we just conjecture that all the entries are algebraic integers, and we prove that they are algebraic numbers, as we showed. And so algebraic integers, and Tsachik Shapiro gave this definition with a compact kernel and a rational structure on H that I said before, and said that and conjectured that. And this conjecture was proved by Margulis. And actually, later was also proved for some rank 1 groups. So the theorem of Margulis is that this is true. High rank. High rank means rank at least 2. Lattices are arithmetic. And I will explain how to deduce this theorem from Margulis superrigidity theorem. Margulis proved for that superrigidity theorem and this is a corollary. And and then actually correlate and Gromov-Shell correlate. Let's see, let me write it. Correlate is double L or double T or anyone knows?
Probably not double L.
Not double L, maybe double T.
Yeah.
Please. So correlate proved the super rigidity for some rank 1 groups. And correlate and then Gromov Shen. Okay, I'm very bad with spelling. So correlate and Gromov Shen. So this was extended also a case for many rank 1 groups. So for subgroup of SPN1 or so there are actually 3 families of rank 1 groups that maybe we discuss in other course. It's the group of isometries of the hyperbolic end space, the group of isometries of the complex hyperbolic end space, the group of isometries of the quinterionic hyperbolic end space, and 1 exceptional group. And in these 2 cases, it's also true that every lattice is arithmetic. This was, I think, this was not conjecture by, I think it was not conjecture even by Petersky, Shapiro, and Selberg, but it's true due to the work of Corley.
What's that sign about the
Sorry?
What's this?
That's an exceptional rank 1 group. It's a group of isometries of the octonion space.
I know that for this, it's written.
Minus 20. F4 minus 20. So that's the exceptional rank 1 group. There are 3 families. So these are super rigid and arithmetic. So all the.
Is it algebraic?
Sorry?
Is it algebraic?
Yeah, they are algebraic groups. They're very similar to higher rank groups in the sense that, for instance, they have property T. They don't have the normal subgroup theorem, but there are some similarity and there are some differences. Anyhow, the 2 cases that remain are SON1, the isometries of hyperbolic space, and SUN1, the isometries of complex hyperbolic space. Actually, in this group, it's still true, surprisingly, by completely different reasons, that the entries of that if you have a lattice, then the eigenvalues are algebraic integer, not just algebraic number. But here it's probably false. We don't know. I don't know if examples are known, but anyway, soon there will be this Yoram seminar after Yoram Lindenstrauss, and Uri will be the main speaker, and he will speak about something related to the arithmeticity of subgroup here. Okay. You should come to the seminar and go there next month. Anyhow, that's the arithmeticity. That's a bit about the arithmeticity. We will discuss it more in future lectures. Okay, so let's go back to the other application I wanted to say about local rigidity. So I will slow down a bit and try to be more elemental. So as I said, like two main consequences of local rigidity, or my 2 favorite consequences. One is this Selberg theorem about algebraic entries, and the other is one that's finite. 72. So a lot of interesting stuff happened that year, one finiteness, like its alternative. The super rigidity that the arithmeticity theorem that I mentioned before was proved by Margulis in 71 for non-uniform lattices. But it took like 4 years to check the paper, so it was only published in 75. And during that time, in 73, actually managed to prove the super rigidity and arithmeticity for uniform lattices, which is much more difficult. Okay, if you look at the histories of the proofs for non-uniform are much longer, but the proof for uniform are much more ingenious, I think, and also apply to non-uniform. So, and that's what we learn. So in modern time, nobody looks at the original proof for non-uniform because it's long and complicated, but the papers are very, contain a lot of interesting lemmas. So there is a long paper by Margulis. There's also a long paper by Raghunathan, maybe 200 pages, which proves the same result, arithmeticity of non-uniform lattices, but he was missing one ingredient, which Margulis could prove, and it was recurrence of uniform. And okay, so this all happened a long time ago. Also this one. So what? But this is much more straightforward elementary theorem, which says the following. So let B be let's say let me say simple. You can also there is a version for semi-simple, but you have to argue with some SL2 factors, which so suppose G is not locally isomorphic, SL2R and SL2C. Suppose that it's not one of those. Then, for every V, there are only finitely many lattices G of volume, of co-volume. So this says this is not true for these two words. And it's true in any other. In particular, it follows the corollary, example of corollary, there are only finitely many hyperbolic, let's say, 4 manifold volume most. For every V, there are only finitely many hyperbolic manifolds, complete hyperbolic manifold of volume less than V. This is not true in dimension 2 because you have type Miller theory. There are only finitely many topological manifolds in dimension 2, but each of them has continuously many hyperbolic structure. In dimension 3, each hyperbolic manifold has unique hyperbolic structure. This is most of rigidity, which we will also discuss soon. But there's still so remark. There are countably many free manifold hyperbolic of volume bounded by the EPs. So there is always a lower bound. You cannot find a hyperbolic manifold of arbitrarily small volume. This is the Gelander theorem, which I mentioned, which we discussed in the past, but I mentioned soon because we need it for one theorem. So there is a lower bound on the volume, but once the volume is big enough, it's in dimension 3, you can find countably many. But in dimension 4, there is only finitely many, and then you can ask about the growth, how many, and you can ask a specific question. We will come to that.
Tsachik, it means that if it means that lattices can't be very close to each other.
This is local rigidity. Local rigidity says that lattices cannot be very close to each other. But here it's more than that because yeah, it's related. So what happened? You see, what you said is related to local rigidity, but local rigidity applies for, let's say, uniform lattices in C. And this theorem countably many hyperbolics, even compact. You can find countably many compact hyperbolic tree manifolds, which are so. What happened is that you need local rigidity, but not just for compact. You need them also for non-compact. Because what's happened is that in dimension 3, you can have a sequence of compact manifold that converge to a limit which is a non-compact manifold. And all of them, the limit is volume, and all of them is smaller volume than the limit. So you can have such it's a complicated construction due to Thurston, but you will see where local rigidity comes into the game. So,
And it fails on dimension 4. This construction fails in dimension 4.
Yes, yeah, that's a very interesting remark. It's called hyperbolic dense surgery. It's something very three-dimensional. So yeah, it's very dimensional. Actually, I wrote with Nicolas Bergeron a paper exactly about that many years ago, about why you cannot have surgeries in higher dimension and how to use local rigidity from that. Let's so how do you prove? So that's one of the nice things is the proof here. So you prove finiteness by showing that with respect to a certain topology, this set is both discrete and compact. So so the ingredient of the proofs are the proof relies on one. Compactness criterion. I remind you, Chabati, it's called a Chabuti compactness criterion. I call it Chabuti Mahler because it's the same as if you know Mahler criterion. So Mahler compactness criterion is about lattices in Rn. You consider the space of lattices in Rn of unimodular lattices. So lattices for volume 1, you actually can think of it as the quotient SLN R modulo SLN Z. That's the, you can see the space of all lattice unimodular lattices in Rn, because SLNR takes transitively on lattices in Rn, and SLNZ is the stabilizer of the standard lattice. So the quotient is, and Chobati and Mahler criterion is about compactness of subsets here. And what he says that a set of lattices in Rn is compact if and only if there is some identity neighborhood that all the lattices miss. If you look all on lattices in Rn, but of volume 1, of covolume 1, and so the only way that you have a set of a non-compact set to go to infinity in this space, the only way is that if you get what is called a very tall thin lattice. So it's a lattice with fundamental domain which looks like that. So that's the only way to go to infinity is to get lattices with points. So every lattice in R2 is a cyclic, is Z cross Z. But the Z cross Z can have a very short vector, which says that the other one should be very long because the volume is 1. And that's the only way to be. Otherwise, any other set is common. It's relatively common. Okay, so that's a Mahler criterion, and I generalized it last time. Chabati generalized it, and the criterion says, okay, let me write. Okay, the criterion says that the following. So let gamma n in G be lattices. Now G is any of all. Okay, let's. So let G be a local compact group. O in G an open set, and V some number. Then the set of all gamma in G such that gamma intersect O trivially, and the core volume is bounded by V, let's say, is complete. That's the Chabati compactness, which is exactly like Mahler criterion, but for general G instead of for Rn. Okay, so we discussed it. Are you happy with the proof of that? Or Tal was not happy for a few days, but maybe now he's happy. What? So should I explain again why?
Always happy or always happy?
What?
No, I don't want.
What you want?
Does the proof use local rigidity?
No, for this you don't need local rigidity. So that's one of the ingredients in one finiteness theory. I tell you that you prove one finiteness by showing that the set of lattices after conjugacy as a topology with respect to which it is both compact and discrete. So this will be used for the compactness side and local rigidity for the discreteness side. So I'm writing the ingredients of the proof. So should I explain why this is true, or you're happy?
I didn't completely understand that.
You didn't understand.
No, this one thing, it doesn't matter. I don't want to repeat the one.
Let me briefly repeat the compactness criterion. So I don't know. Somehow we missed the break because of the beginning. So should we have like a 5-minute break or?
Yes.
Okay. So after the compactness, yeah.
I understand.
Sorry?
I said, we understand the proof.
Should I recall the proof? So the proof relies on the following. So if gamma n, let's say gamma n intersect omega trivially, then gamma n up to a subsequence converge to some limit, and the limit also intersect this trivial. And so that why it converges to a limit, because the space of all closed subgroup is compact. Space of all closed subgroup is compact, so any sequence of closed subgroup has a limit, or we're going to subsequence. Now, if all of them intersect this set trivially, then also the limit must intersect. That's a so in particular the limit is discrete.
That's a good.
Yeah, that's it's all distributed to do this converge. And so that's one thing. But also the core volume of gamma is the supermum of the Haar measure of K, where K is a subset such that K inverse intersect gamma, K inverse K intersect gamma trivial. So I explained this last time. So this is how we compute core volume. So the supermum of that, and so take such a K, take K compact such that K inverse K intersect gamma trivial. Okay? So you see that K inverse K minus O intersect gamma empty. The intersection is empty. Which implies that K inverse K minus O intersect gamma n in the empty set for large n. Because this is closed compact set. So if there was non-trivial intersection, it would pass the limit, which implies that K inverse K intersects gamma and K in the trivial n. Because which implies that the core volume of gamma n K is at least the Haar measure of K, which implies that the Haar measure of K is smaller than. We want to show that the limit is still intersect O trivially, that's obvious, but also it has core volume at no limit. So that's the proof of the combined scheme.
You know, it just like last time you said that even if you don't have one single O which intersect trivially, then still the covolume of gamma is at most the limit of the sequence. You need to assume that it was just
no, this is true. This is true only, no, I don't know if only, but it's not true in general. But it's true. No, it's not true in general, because you can take, if you have even a compact cofinite group, you can have a, it's not true. Let me repeat the exercise. It's true for Lie groups. It's true for Lie groups. Yeah, what I just said, it's true for Lie group, but it's not true for totally same. Because and the property of Lie group that makes it so that Lie groups has no small subgroups. And when you have no small subgroup, okay, then you can. Okay, so this is the compactness criterion. That's the first ingredient. Let me just write the other ingredient. The second ingredient is Weizmann theorem. Says that there is, let's say it's more general, it also applies for 1 and 2, so let G be a semi-simple Lie group. By the way, it also was one of the steps, I didn't know it, but now that I read Margulis' lecture note for his Abel Prize lecture, so we say that they proved this theorem as one of the steps that, like Selberg and Petresi Shapiro had like a program of how to prove arithmeticity of non-uniform lattice. And it relied on the existence of uniprot. So they wanted to show that every non-uniform lattice admits uniprot without assuming it's arithmetic. And this okay, and this was the first step to do that. So Margulis proved the following. Okay, the term that I'm going to use is defined. So there is an identity neighborhood U such that for every discrete group, you don't even need it to be a lattice, there is G in G such that G gamma G inverse intersect U3. And this, again, in my previous courses, I gave like 3 different proofs of that. We will mention one proof of this when we discuss invariant subgroups, so it's few-line proof. But I also, I think, explained Gromov's geometric proof at some point for that. So there are 3 different proofs of that. The theorem. So in particular, this is a quite fantastic theorem. It's not very hard, but it's quite fantastic. It implies the minimal covolume statement, so that if in dimension, even in dimension 3, there is a lower bound on the volume of the hyperbolic manifold. Because of that. And it's so in M for any Lie group. So for any Lie group, there is a lower bound on the covolume. For any semi-simple Lie group, there is a lower bound on the covolume of lattices. So that's Margulis' theorem. And you see, if you combine both this and the compactness criterion, it gives you the compactness that you need. The other 2 ingredients, let me just write them. 3 is lattices are finitely generated. And 4, and this is lattices in Lie group. Lattices in Lie group. It's not true in general for group, as we know, but in Lie group lattices are. And this is also like a non-trivial theorem. It was like an open problem for some years and proved by many different people by case analysis. And yeah, but okay, now there are also geometric proofs. And the last ingredient is local. Okay, and now we'll have 5 minutes break because we started 15 minutes late. So, but after the break, I will show you how if you combine these 4 ingredients, you could multiply one.
צחיק,
כן.
last time, פעם שעברה אמרת שזה ל-connected semi-simple לגרופ.
So,
לא, לא צריך
Okay, so let's explain how these four things together. Huh?
About connectedness, how this works in SLM.
You ask, what about SL and QP? Yes, it's true. Okay.
But are you talking about one finite theorem or
Cardano-Goulis theorem is trivial for SLQP. Exercise. Right now, really, it's very easy for PI groups. Compactness criterion is true. Lattices are finely generated is true. And local rigidity is also true. Except for SL2, which is not true. In SL2 QP, it's not true, but for higher dimensions. Now, several years ago, Ariel Levitt and myself generalized local rigidity to very general situation of group of isometries of cut zero spaces. And it's still true in that very wide generality. And we deduce some version of one channel. Even, okay, but you need some form of Cardano-Goulis. Anyhow, so let me now explain the proof, which is very elegant, I think, and gives no effective information at all, which is actually one of the cool things about this. Okay. So proof of one cube. So consider so let omega v be the set of lattices in G of co-volume V up to conjugation. Do I want that? Basically, I want to show that this set is finite. But another way is not to say up to conjugation, and then I want to say that it's covered by finitely many conjugations. So, okay. So, okay, let me, there should be a cool way to write it, but I'm not going to do it. I will do it in the most straightforward way in the way that I see it, that I think of it, but if we write a book, then in the book it should be more like, here is the topology, this is why it's compact, this is why it's discrete. And it's compact because of 1 and 2, and discrete because of 3 and 4, but let me now write it without saying. So, suppose, by way of contradiction, that gamma n side G on a lattices non-isomorphic, non-conjugate lattices of volume bounded by something. I suppose that there is such an infinite sequence, and I will deduce contradiction. By Cardano-Goulis, by item 2, which is Cardano-Goulis, we may suppose that gamma n intersect U trivially. Right, I can replace it by some conjugate, such that it's trivial. And then by the compactness criterion, up to taking a subsequence, replacing by taking a subsequence. I will not use gamma n k, I will skip gamma n. Gamma n converge to a limit. And gamma is the lattice of covolume mod V. Now I will show you that gamma n must be conjugated to gamma. So actually, let me. We don't need it. But lattices are. Let me change. I can treat lattices are finely presented, which is also true. But lattices are finely presented. Finitely many generation, finitely many relation, but it is not needed here. I will later ask you as an exercise to do it without the finite presentation. You see, you would want to say, okay, now it follows from local rigidity of gamma, right? Because if gamma n are sufficiently close to gamma, then it must be conjugated to gamma by local rigidity.
Mm-hmm.
This is local rigidity, but local rigidity was with respect to the representation variety. And the compactness was with respect to the Chabuti. So I need to relate these two topologies. That's why I need this finite presentation assumption. By the way, in the paper that I mentioned with Ariel Levitt, we also proved Chabuti to local rigidity, which you could apply here directly, but okay. So let gamma be, let sigma r be a presentation of gamma. Now notice that if gamma n is very close, so it's Chabuti, about to very close to gamma, there is a map. The map Fn from gamma to gamma n, sending sigma to the nearest element, for sigma in the generating set. So it's, this is how I define it for a finite set. Will satisfy the relation in R. So it's not a homomorph, it's a priori not a homomorphism. I just tell you what to do to each generator. I have a group gamma, which is a limit. Okay, this is G, and inside G, I have a group gamma, which is a limit of some sequence of groups. Let's say that I have a blue group, which is very close to the black group. The black group is the limit of blue groups. So it means that if I look at a large ball inside G, near every black point, I see a blue point. And I don't see other blue points. All the blue points are close to black. So now I look at the generators, and each generator I send to the nearest point. If there are two, I just choose randomly one. So each generator, they actually cannot be two. If it's sufficiently close, you can show that it cannot be two, because what's happened is that both blue and black groups miss some identity neighborhood. So near every point there is only one which is very close.
What do you mean we'll satisfy the relations now?
And what is a relation? A relation is some word in the generator. Let's say the sigma 1 cube, sigma 2, sigma 1 inverse, sigma 4. That's for instance a relation. Now if I send them to something each sigma I move a bit, I deform to some blue element which is close to it. So this relation maybe it's not satisfied, but it must be close to the identity.
In G.
In G. Now, it's in G, but it's also in the blue group.
So it must be identity.
It must be identity because the blue group misses this identity.
So R must be bounded? Like,
Yes.
So
I assume that R is finite. I assume it's a finite presentation.
Ah.
I assume it's a finite presentation. So yeah, I changed the item to finite generation to finite presentation. But it's true, lattices are finitely present.
So finite presentation tells you that there are finite generators and finite
Both
relations.
sigma
Oh.
and R are finite. Yes, that's so every lattice in a Lie group is finitely presented. That's true. And I'm kind of using it here. And so that every relation is satisfied. Once every relation is satisfied, this map, which was a priori just a map, it's a homomorphism. So now we know that F is a homomorphism which is close to the identity. Then Fn is a homomorphism close to the inclusion. Why? Because that's how the topology is determined, or what do you do to the generator. So if every generator is moved by a bit, then it's close to the inclusion. And so by local rigidity, by 4 local rigidity, Fn is
It is closed by which topology?
sorry?
So you said Fn is close to the identity,
Yes.
but by which topology?
No, now close in the identity, the representation variety. Now I consider the topology of from gamma G. The topology here is just the point-wise topology. And if every generator is moved by a bit, then that's it.
So I need to say that if it's injective, then the inverse should be.
So I don't know that F is injective.
So Fn should be a map from from gamma to gamma n.
Yeah,
Okay.
Fn is yeah.
That's the direction.
I take every generator to a nearest point, and then I say because gamma n miss this open set, then every relation must be almost the identity and therefore the identity. So all the relations are satisfied, then it's homomorphism, and by definition it's close to the inclusion. So by local rigidity, the conclusion. So you get that if you want to get that gamma n contains a conjugate of gamma. But it must be equal because the core volume of gamma n cannot be smaller than the core volume of gamma. So if you want to finish the proof, you say this implies that gamma n contains a conjugate of gamma, but since so if it really contains, if it's not equal, but for large n, the co-volume gamma n is bigger than the co-volume gamma, let's say, than half of it. So it cannot be. So this implies that the gamma n is conjugate.
Why do you say it contains and not is a conjugate one?
Because you have a map from gamma into gamma n. I don't know whether it's surjective a priori, but then I say if it's not surjective, then it's of index at least 2. So the co-volume of gamma n is at most half. But since co-volume just decreases in the limit, it's going to. So gamma n is a conjugate, and this is a contradiction. Because we assume that gamma n is not conjugated to each other. So if they're all conjugated to gamma to the limit, they're conjugated to each other. So that's a proof of one theorem. I find it very elegant. Any questions about it? So
Sorry, I'm just going back. So F maps the set of generators to something that also satisfies R, but that's going to be another element in the blue group, which is also in U.
So
Do you mind just going over that argument again? So the set of generators is taken to the closest element, right? And that has to satisfy the relation, because when you apply the relation to it, you get something close to the identity. And that must be the identity itself.
yeah, it must be identity because
It's in the blue group, not the black group.
yeah, but the blue group also miss you. The assumption we started, we say that if you remember, we started by let's gamma n be lattices probably possibly. By Kashdan Margulis, we can assume that we can conjugate each of them such that they will miss the u.
Okay.
So gamma n miss u. And okay.
For any n or
Yeah. For any n.
so this is the same u for any n.
Yeah. The u is just Kashdan Margulis. Kashdan Margulis neighborhood, any discrete group you can conjugate to miss it to intersect the trivial. So
But gamma n are actually conjugacy classes of lattices, right? I mean,
sorry?
gamma n you consider like
Yeah, the theorem is that there are only finitely many conjugacy classes.
conjugacy.
On finitely many lattices after conjugation. That's the theorem. So the exercise that I wanted to give to Tal is to write this proof nicer. So not to use this gamma n and choices, but to say what is the topology and why this topology, why this set is compact and the direction. Okay. That's how it should be.
How did one write?
What?
How did one?
No, one I think did something like this. I think you can look at it. So by the way, this is how I started my PhD. So when I was a PhD student, I came to Shachar, my advisor, and told him that I want to study lattices, and said, okay, read this, and this, and let's meet. So we met again after a year. No, we met a lot, but after a year, he said, okay, now I have a problem. And the problem was to get effective estimate. So one tells you that it's finite. This proof gives you no clue what is this number. So you need to find another proof Yeah, and which gives you something. Okay. So that's one connected theorem, and I said finite generation is enough. So let me write an exercise show that the proof requires only finite generation rather than finite permutation. And so that the exercise and the hint use Hilbert basis. So what is Hilbert basis theorem is that the ring of polynomial is Noetherian. So every ideal is finitely generated. So basically, this Hilbert basis theorem says that from gamma G, this is algebraic variety. So algebraic variety is determined by finitely many polynomial. So this is actually the same as from gamma tilde G for some gamma tilde, which is finitely present. So if gamma is for gamma finitely generated, now this is true for any finitely generated group. I don't think, even if gamma is not a lattice, take any finitely generated group and consider its variety of presentation into some given semi-simple group. Then this is an affine variety, I'm using that. So this variety is the same as another variety, where this is a very bigger group. It's a group with less relation. It's useful exercise. It's, in that case,
but you still have local integers. So the map is no longer injective, which is local.
Yeah, I mean this. In general, you can consider home gamma G for any group gamma. If gamma is not linear, then no maps here will be injected. So this is true for any. But the fact, I think it's a useful fact that any representation variety is actually can be considered as a representation variety of finitely presented.
Hold on, we've assumed in the statement of the theorem, we've assumed that she is a connected semi-simple B group.
Yes.
Does that already mean that it's a set of real points of observation?
Yeah, let's say adjoint group. So let's say adjoint. Let's say connected semi-simple adjoint group. So every such group is a algebraic group. I'm using it many times without. I'm using fact for lithium, but this is not a hard fact. Every adjoint group. Every adjoint center free. Real semi-simple Lie group is a real right group. But you need center free because if it's not center free, then it's not true. For instance, I mentioned the universal cover of SM2R, which is not algebraic. because it has infinite center, if you want. So you know the fundamental group of SL2R is just cyclic. But another interesting fact is that also the universal cover of SL3R is not regular. And this is just a two cover. So this is the center here is just there are only two elements in the center. So SL3R is homotopically equivalent to the projective tree space, which is SO3. So the fundamental group of SL3R is just a cyclic group of order 2. So the universal cover is a degree 2 extension, but still it's not linear. You don't have faithful linear computation. I think it's what I said. So anyhow, so it's not true that every semi-simple link group is algebraic, but every set of field very ideal. But this theorem about lattices usually okay. This finiteness theorem allows you to divide by finite center, and so it's okay if we assume a joint. So yeah, Selberg proved local rigidity. People, it's more famous as was Whale local rigidity theorem. Whale or Whale, I never know how to say. But because it proved the general case, but it seems to me that Margulis gives credit to Selberg because first Selberg was the first, although he didn't consider the general case, and secondly, Selberg's approach was very influential. Actually, in some sense, it started this beautiful theory of rigidity and arithmeticity. And in this paper from 1960 of Selberg, you can find plenty of interesting lemmas. Most of them are elementary, but very, very beautiful. In particular, this what people do remember from this paper is Selberg lemma that every linear group is finite. A finitely generated linear group is virtually torsion-free. It means a finite index sum which is torsion-free. But there are many of other interesting lemmas in this paper. Now, some years later, Mostow proved much more impressive and extremely strong results about rigidity, which is the second rigidity theorem that I want to discuss. And this is one of the maybe I would dare to say one of the biggest jumps in mathematics in the previous century. It's really like an amazing theorem. And okay, let me paint it. And so it's called strong rigidity. So most rigidity, people call it strong rigidity.
Why is it called strong rigidity? Like weak rigidity? Just rigidity?
I don't know. Actually, I don't know why it's called strong rigidity. I know why Margulis theorem is called super rigidity. So the story that I heard from Mostow is that Margulis was invited to the ICM, to the International Congress. I don't remember where it was, but also Kashdan was invited, and they were in Russia, and then Kashdan didn't arrive to his talk, and then they understood that probably also Margulis is not going to arrive. They were not allowed to go out of Russia. So the day before the talk, they asked Mosto to explain. Margulis submitted a paper, and they asked him to give the lecture instead of him. And so he was awake all night reading it, and said that this was super good. So he was amazed by the strength of the results, proof of supergidity and arithmeticity, and he named it supergidity. But it was already, the name strong rigidity was already given. But so the theorem of Mosto is the following. So let me say it in a very general case. So some of the cases are not due to Mosto, but for the Partizan. So this is the theorem. So let be same simple Lie group. Again, not locally isometric, isomorphic to SL2R, but you allow SL2C. So in a sense, you will see that it looks stronger than local rigidity, but it does not imply directly local rigidity. Let gamma 1 and gamma 2 be lattices in G. So local rigidity say that if they are sufficiently close, then they are conjugate with respect to some topology. So if there is a map from gamma 1 to gamma 2, which is close to the identity, then they are conjugation. And most of say that you don't need to be. If F from gamma 1 to gamma 2 is an isomorphism, then F extends, F or F extend, or F is a restriction of an automorphism. Extend to an automorphism of G. Now the group of automorphism of G is basically G itself. So any automorphism is, there is, it's not precisely true, but of course there are the inner automorphism, which is the group of automorphism of G is some finite group of outer automorphism. Out G in direct in G.
It's really same direct point.
Okay, let's out G. Yeah, it's okay. Maybe, but this is finite. That's what this is a out G. It's finite, and the inner automorphism G is, if G is center free, then it's actually G. So we want to add G modulo the center. If G is center free, then it's so basically it's almost true to say that if you have two isomorphic lattices, then they are conjugated. They could be conjugated by an automorphism, but there are infinitely many such. So
That extends uniquely.
sorry?
Extends uniquely. Non-morphism
Yes,
is during
extends
Ben's value.
Yes. And then F extends uniquely. This is it's quite remarkable, I think. It's related to the what's called the Whale Conjecture. So if you want another version of it, so corollary. Let me say it very focusedly, but you can say it for every locally symmetric space. So so let's let M1, M2 be finite volume hyperbolic, let's say 3 manifolds. If fundamental group of M1 is isomorphic to the fundamental group of M2, then M1 and M2 are isometric. And instead of, you can say it's not just about 3 manifolds, but any locally symmetric manifold. You have 2 locally symmetric manifolds of the same type, they're the same universal color. If they are isomorphic, if they have the same fundamental group, then they are isomorphic. This is algebraic topologies. There is a very famous conjecture called the Whale Conjecture that says that for certain manifold, maybe aspherical manifold. So for certain manifold, if they are homotopy equivalent, then they are homeomorphic. So Mostov proved it for locally symmetric manifold, but he proved much more than that. He proved that if you have 2 manifolds which are homotopic, then they are actually isometric, they're not just homomorphic. Why this is homotopic? So a fundamental group is the first homotopic group, but the higher homotopic group of such manifold are trivial. So to say that the 2 such manifolds are homotopic is the same as saying that they are the same fundamental group. So if they have the same fundamental group, they're isometric. That's an amazing theorem. So it's really amazing, and I think it has even more influence on mathematics than superrigidity. I think because superrigidity is which I'll come to is the strongest result, is the holy grail in the theory of lattices and arithmetic groups. But this theorem applies to hyperbolic manifolds, for instance, which many people are interested in hyperbolic manifolds where superrigidity do not apply. Yeah, but one remark is that it does not directly imply local rigidity, because you see, it is true for non-uniform lattices in SL2C, for 3-dimensional hyperbolic manifolds which are not compact. While local rigidity does not apply. So it seems stronger than local rigidity, but it's not directly implied local rigidity. It's something else, but most of it was influenced. In some sense, this is also a beginning of the boundary theory, because the proof of Moscow is by extending maps. You have maps between 2 discrete groups, you extend it to some of the boundary of the symmetric space, the Tits boundary, the Tits building, which we discussed last year. Every symmetric space has some very nice spherical building, which is related to flex variety. And most of them show that, okay, in some sense it's yeah, okay. How to extend, how the map is extended to automorphism of the Tits boundary, and then we apply some theorem of Tits, that every automorphism of such a building is not a field of a group. But the theorem itself, it took him several years to publish the proof. I think first he wrote a proof for a compact hyperbolic manifold. Later he wrote a proof of a higher rank manifold, which is it's actually a book. The book has the strong rigidity for higher rank manifold. It's actually a book, and it almost shows arithmeticity. It's almost so super rigidity, but it doesn't. And he told me, Moser told me that the most difficult case for him was the rank one, which are not able, like SU1, SPN1, and F4-1. But he managed to prove it, but some years later, the Sonport and Galo gave a much shorter proof for that case. The cases of rank one manifold, which was hard for him, it's easier in a different approach. I should remark that the case of non-uniform lattices in rank one is due to Prasad, not to so strong rigidity for that case is due to Prasad. Anyhow, this is an amazing theorem. So I see that this introduction to rigidity goes longer than I thought. So if I will follow my initial plan, so next time I'll explain to you some application of this strong rigidity, and then I will explain super rigidity and arithmetic in a bit more detail. But I will ask you if you want that. The other alternative, no, I think maybe it's good to say a bit more. So let's try to start on time next time. So and then we have a proper break. And